Yo-ho, yo-ho, a pirate's life for me. Oh. Hi, I'm Walt Disney Imagineer Asa Kalama. I'm one of the people who design and build all the cool theme park attractions. Like this one, Pirates of the Caribbean at Disneyland. It's a wild, swashbuckling adventure into the pillaging pirate world of trickery, skullduggery, and treasure. But I know what you're thinking. Pirates of the Caribbean may be an all-time favorite.
Here, doggy.
But Asa, isn't this supposed to be a show about science?
Ow.
Well, it is. As Imagineers, we use science to tell stories to take you to exciting places. And when you start thinking like an Imagineer, you're gonna find that science is really a lot like this. And this, and this. So avast, me knowledge-seeking buccaneers. It's time to set sail into the world of imagination, inspiration, and science. As we dream it, do it. The science of Imagineering. Don't worry, there be smooth waters ahead. Yar! Hi, everyone. Welcome to my workspace at Walt Disney Imagineering Research and Development. The place where imagination meets engineering. Something I've been working on. I'll show you more in a minute. But that glove does have a little something to do with the science we're looking at today, which, if I may warn you, is kinda repulsive. But on the flip side, literally, it's also quite attractive. Yes, today it's both, as we explore the magical and sometimes mystifying world of magnetism. Yes, magnetism. That odd, pushy-pulley force that not only allows us to stick all kinds of things to our refrigerators. What? I like pudding. It's also responsible for a lot of other things that are happening in the world around us. Like when you buy something cool with a gift card or credit card. This little strip on the back uses magnetism. When you turn on a fan, or a hairdryer, or a vacuum cleaner, the electric motors inside spin around and around thanks to magnetism. That horrible sound you hear through your speakers is also magnetism. I just sucked up a tennis shoe. Even something as simple as a computer storing information on its hard drive is done using magnetism. But what exactly is this mysterious force that seems to do so much? Magnetism is the force of attraction. Not that kind of attraction. It's the force of this kind of attraction. Or repulsion in a material. And any object that exhibits those magnetic properties of attraction and repulsion is called, yes, a magnet. While most things don't show strong magnetic properties, like bananas or a rubber ball or an angry rhinoceros, some metals are very strongly attracted to magnets. We call them ferromagnetic, and they themselves can actually become magnets. Metals like iron and metals containing iron, like steel. Magnets were first found in nature, like the magnetite rocks discovered by the ancient Greeks. Magnets can also be human-made in all different shapes, sizes, and strengths.
Boola, boola.
In fact, it's the powerful pushy and pulley force of magnetism that has today's scientists working hard to make stronger and stronger magnets. Magnets that may one day even launch a vehicle into space. Good luck! But those are really strong magnets. Yes, magnetism really is all about attraction and repulsion. And speaking of attraction, this is a bar magnet. And this, well, it's just a piece of string. And this is my finger. Right now, this bar magnet is experiencing some pretty strong attraction. This end is actually being attracted to our planet's geographic North Pole. The other end is being attracted to our planet's geographic South Pole. This strange magnetic behavior is something our early explorers discovered and used to make the world's first compasses. It also led to the very important understanding that every magnet has two poles, where the attraction is the strongest: a North Pole and a South Pole. Not this pole. That's the attraction part of magnetism. The repulsive part comes into play when you bring two magnets and try to stick the same or like poles together. North and north don't want to touch. Neither do south and south. You get that weird pushy feeling as they try to repel each other. But put the opposite poles together and it's like it was meant to be. There's definitely attraction here. The rule for magnetic poles is like poles repel and opposite poles attract. But wait a minute. If like poles repel, then how can the North Pole of a compass needle be attracted to the North Pole of our planet? It can't. It's time for
an odd but true magnetic fact.
Our planet is a giant magnet with two magnetic poles, one at geographic north and one at geographic south. And when early explorers named the end of the compass needle that was always pointing north, they were right in doing so. But these ancient mariners didn't really understand magnetism in those early days. The truth is, our planet's geographic North Pole is really our planet's magnetic South Pole. And our planet's geographic South Pole is really our planet's magnetic North Pole. Wait, let's hear that one more time. Our planet's geographic North Pole is really our planet's magnetic South Pole. And our planet's geographic South Pole is really our planet's magnetic North Pole. Just remember the rule. When it comes to the attraction and repulsion of magnets, no matter how big or small they are, opposites always attract, and likes always repel. Now, I know what you're thinking, because when I was younger, I always wondered about it too. You're saying, Asa, sure we felt that pushy-pulley feeling between magnets, but can you please tell us why that happens? I sure can. All I need is this magnet, this piece of glass, and the sheet metal shop here at Imagineering. Oh, and a few teeny little pieces of iron. I went ahead and taped the magnet to the back of the glass. And by holding it under this shower of magnet-loving ferromagnetic iron filings, a very cool and mysterious force will now reveal itself. See how the iron filings have formed a pattern around the magnet? That is the magnet's magnetic field. Every magnet has a magnetic field. It runs in a loop from the North Pole to the South Pole, through the magnet, and then around and around again. You can also see from the concentration of iron filings that the field really is the strongest at the two poles. That pushy feeling you get when you try to put like poles together is the magnetic fields trying to turn the magnets the other way to make their field lines line up in the same direction. Here, you can actually see the field lines trying to line up and pull together when opposite poles are attracting each other. And here, you can see the repulsion, the swirling away of the field lines, when like poles are placed near each other. Just think of it this way. Every magnet wants to line up with other magnets to make even bigger and bigger magnets. Thanks for the iron filing.
Here, I made you something.
Wow, very impressive and magnetic. So if little magnets want to line up their fields with other magnets to make bigger and bigger magnets, Is it possible that little magnets are made up of even littler magnets, and so on, until they get so small, you've got magnets that you can't even see? The answer is yes. In fact, it's these teeny tiny itsy bitsy magnets that make a magnet in the first place. It's time to take an amazingly close look at, not at me, at atoms. Magnets, like all other things in our universe, plastic toys, trees, chickens, fruit pies, you and me, everything is made up of tiny little particles called atoms. Many people imagine atoms looking like our solar system, the sun being the positively charged nucleus of the atom, and the orbiting planets being the negatively charged electrons. Are you ready for this? Electrons are actually the world's tiniest magnets. See, whenever a charged particle, like an electron, moves, it creates a magnetic field. Now, with most atoms, like the ones in plastic toys, trees, chickens, fruit pies, and you and me, electrons orbit in pairs and spin in a way that cancels out the atom's magnetic field. And that's a good thing, because if every atom in our universe was a strong little magnet, well, let's just say we wouldn't get much done. Now, when it comes to the atoms of a magnet, there are actually electrons spinning by themselves. So there's nothing to cancel out their magnetic fields, and the atoms become little magnets. Now, don't forget, all magnets, no matter how big or small they are, want to align their fields to make bigger and bigger magnets. And that's exactly what the magnetic atoms do. Quintillions of magnetic atoms align their fields to form bigger magnetic clumps called domains. And domains, yep, you guessed it, they also want to become bigger and bigger magnets. So they too align their fields. And before you know it, the electrons have aligned, the atoms have aligned, the domains have aligned, and you've got a magnet you can do something with. And this is why you can cut a magnet into any number of pieces and still end up with each piece having a north and south pole. The smallest piece will always be an electron, and that is magnetic all by itself. Atoms are the whole reason a magnet sticks to your fridge and to other metals. The atoms in both the magnet and the fridge door are looking to align their fields to make bigger and bigger magnets, which the atoms do when the magnet sticks. And speaking of magnets that stick, these gloves are part of something fun that I've been working on. It could even be a new guest experience one day. Think about this. How cool would it be if we could actually climb walls like a superhero? Well, thanks to magnetism, maybe we can. This is a magnet-loving steel wall. And these gloves and boots contain super strong magnets. Now, just like with our refrigerator, the atoms in both my climbing gear and the steel wall will want to align their fields to make me stick. But will it work? Let's find out. I just have to be really careful with these magnets because they are so super strong. Seem to be a little stuck here. Well, while I try to figure this out, let's go take a look at some of the many ways we use magnetism in our theme parks. Or as one magnet said to the other magnet, come on, stick with me. I'm okay! Magnets of all types can be found throughout our theme parks. Sometimes we use magnets to move people. Magnets are at work here too. We use these magnetic connectors to help direct our guests through all sorts of fun attractions, like the ones here at the Seas with Nemo and Friends. Permanent magnets, as the name implies, are always on, always attracting and repulsing. Like these name tags. They stay attached thanks to permanent magnets. But these aren't the only type of magnets we use in our theme parks. Sometimes we need to be able to turn our magnets on and off. Like here at the Astro Orbiter at Tomorrowland. No. The magnets aren't up there. They're right down here, at the exit gate. See, to keep everyone safe, we need to be able to control when the gate can open and when the gate needs to remain shut. For that, we use an electromagnet. An electromagnet is a temporary magnet that only becomes a magnet when electricity is applied. Electricity is really nothing more than electrons moving through a wire. And when electrons move, they create a magnetic field. So a wire with electricity flowing through it naturally has a magnetic field. By coiling that wire around something like an iron rod, the atoms in both line up their fields to make a bigger magnet, one you can turn on and off when you need to. This is the electromagnet right here. And this is the steel plate it attracts when the electricity is turned on. Now, it may not look that big, but electromagnets can be very strong. Using the same amount of power that a nightlight uses, the attraction between the electromagnet and the steel plate can withstand about 1,200 pounds of pull. Yep, safe and secure. While electromagnets can be used to keep doors closed, they can also be used to open the doors to some incredibly fast and furious fun. Rock and Roller Coaster here at Disney's Hollywood Studios is a high-speed roller coaster ride that zips you through twists and turns, loops and corkscrews as you race against time to make it to a rock concert. One of my favorite parts of this attraction is the launch. It speeds you down the track at 60 miles an hour in 2.8 seconds. And behind that high-speed launch are magnets. This is Imagineer Mark Mesko. Tell us how magnetism is being used here.
We've taken the concept of the basic electric motor, like the kind you'd find in a fan or a CD player, but we've done something very different with it and the magnets you'd normally find inside.
An electric motor, like the one I have here from a fan, uses electromagnets placed around permanent magnets. Permanent magnets are always on, always attracting and repulsing. An electromagnet is a temporary magnet that only becomes a magnet when electricity is applied. As the motor's electromagnet is turned on, its poles switch back and forth, back and forth, back and forth to continually attract and repulse the poles of the permanent magnets. This makes the permanent magnets spin around and around, which makes the fan spin. But this is not a traditional motor that's moving the coaster train, right?
Right. We've taken the idea of a rotating electric motor and opened it up, unrolled it so the electromagnets lay flat and stretched out under the launch track. The permanent magnets lay flat on the bottom of the pusher car. So instead of electromagnets spinning permanent magnets around and around, here they use attraction and repulsion to push and pull the permanent magnets forward in a straight line.
And that's called a linear motor. But tell us how the magnets launch the train so quickly.
We've placed two parallel rows of electromagnets under the track. There are 106 in all that are quickly turned on and off in a sequence down the line. Permanent magnets on the pusher car sync up with the pulses of electromagnetism as it moves down the line. In other words, the movement of the permanent magnets on the pusher car coincides with the rate at which we turn on and off the electromagnets. The result, immediate and fast movement down the track.
This system of powerful magnets timed in perfect sequence is similar to what scientists hope to use in the future to launch space vehicles. Now, you mentioned that the permanent magnets are attached to a pusher car. Why not just attach them to the coaster train itself?
To get the powerful attraction and repulsion we need to launch the train that fast, we have to use really big rare earth magnets, 12 of them that are each about 3 feet long. And they are heavy, which means if we attach them to the actual train, then it would have to carry all of the extra weight through the twists, turns, loops, and hills. Roller coasters don't like extra weight. It slows everything down. The pusher car can carry the heavy magnets, provide the force to launch the train, and then remain behind as the train rockets off into the dark. At the end of the launch track, we use the linear motors to send the pusher car back by reversing the current flow in the electromagnets.
Well, what do you say we give it a try?
Yeah, let's go.
Right now, we're about to go 0 to 60, 2.8 seconds.
From magnets that move ya to magnets that groove ya. No, we're not looking for dancing magnetic pirates here at Disneyland's Pirates of the Caribbean. The magnetism we're looking for is the kind you have to listen for. From gale force windstorms to braying donkeys to, of course, pirates, and more pirates. These fully immersive scenes and audio animatronics figures don't just need to look good, they also need to sound good. There are 270 audio speakers positioned throughout Pirates of the Caribbean, each designed to make every scene as believable as possible. And just like the audio speakers you have at home, they're all about magnetism. This is Imagineer Steve Kadar. Tell us why magnetism and audio speakers go hand in hand.
There are a number of important parts in an audio speaker. The basket right here, the diaphragm or cone right here, and these, the voice coil, which is really an electromagnet positioned in the magnetic field created by a big permanent magnet. When a sound is first recorded, it's actually converted into an electrical signal. When that electrical signal enters the audio speaker, here, I'll show you what that looks like with a battery. It changes the poles on the electromagnet to attract or repulse the permanent magnet. The battery pushes the electrons in a clockwise direction, and this makes the entire wire magnetic, which attracts the cone inward. Look carefully at the cone and you'll see it move in one direction. Now watch what happens when the battery is switched and the electrons move counterclockwise. The cone is now repelled because the electrons are going the other way, reversing the magnetic field. As the electric magnet switches back and forth between attraction and repulsion, it pushes and pulls on the diaphragm, which vibrates the air in front of the speaker. That creates the sound waves that reach your ear. Let me show you how this all works with a sound effect from Pirates of the Caribbean. This is the recorded audio waveform. As you can see, it goes up, positive, and then down, which is negative. The audio speaker moves back and forth to follow this waveform. The positive current moves the speaker out. The negative current moves the speaker in. So as it moves back and forth, the cone moves in and out. Let me show you that one more time.
So when the speaker moves in and out really quickly, that's what creates the sound that we hear.
That's right.
And the farther that it moves in or out, the louder the sound is.
That's right.
That's so cool. Obviously, we have thousands and thousands of speakers in our theme parks. There's speakers everywhere. I'm sure they're different sizes for different purposes.
Yes, some are for playing back really low sounds, others work better for high sounds, some are better for mid-range sounds.
It's a speaker. Nah, it's just cotton candy. But no matter what the size of the speaker is, they all use electromagnets and permanent magnets to create the sound that we hear. So what did we learn about magnetism today? Yarr! Well, we know it can both attract and repulse. And when it comes to other magnets, like poles repel and opposite poles attract. Every magnet has a magnetic field. And from the biggest magnets down to the teeniest, tiniest magnets of all, electrons, all magnets want to align their fields to make bigger and bigger magnets. And that's why magnets stick to other magnets and to other materials. We also saw that both permanent magnets and electromagnets can be used to hold things together, to play back sounds through audio speakers, and even to propel vehicles down a track. And we also learned that magnets are strong enough and fun enough to allow for a whole new superhero-like wall climbing experience. And that's the great thing about science. It can take you in any direction. Now that's magnetism. I hope you'll remember that everything starts with an idea. If you follow through with your ideas, science can be the means to turn them into reality. As we say at Imagineering, dream it, do it.